Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 4 on justifying steps in solving an equation. So one thing that's very important as you move on in math is to understand not just how to solve an equation or how to do a particular algebraic technique, but also why you can do it, and to be able to justify it using appropriate terminology and appropriate ideas like the distributive property, the associative property, and things like that. Now, solving equations primarily rests on what we call the properties of equality. So that's going to be the first thing that we're going to look at today, the properties of equality. Let's take a look. So what are these properties of equality? Well, when we manipulate equations in order to isolate the variable, like, adding something to both sides or dividing both sides by a number, we use the properties of real numbers like commutative distributive properties, but we also use the properties of equality. All right, so let's talk about those. The first one that is critically important is called the addition property of equality. And it's real simple. It basically says, look, if I've got some equality, like A equals B, some equation, then A plus C equals B plus C. Basically, it's boiling down to saying this. You can add or subtract the same quantity from both sides of the equation, all right? And you still will have a true equation, right? But the key is, if you add something to one side of the equation, you have to add it to the other side, or subtract and subtract. Now, some people might say, well, then why isn't it called the addition property of equality and the subtraction property of equality? Mostly it's because we don't want to introduce like 4 properties of equality, we just want 2. We want addition and multiplication. And the other one is that if I, let's say, subtracted 3 from both sides of an equation, I could think about that as adding a negative 3. So any subtraction you think about can be thought of as just the adding of an opposite. So if you see subtraction from both sides of an equation, we're going to call that the addition property of equality, which probably seems a little bit ironic. And if you actually said the subtraction property of equality, I don't think anybody would count it wrong, because it is true. You can subtract the same thing from both sides of an equation. We just typically call that the addition property of equality. Now, the multiplication property of equality is sort of the same deal. If I have an equation, if A equals B, then C times A equals C times B. So I can either multiply or divide by the same quantity on both sides of the equation, as long as I don't divide by 0. That's never, ever allowed, ever in math, ever. Anyway, so same idea, since dividing, let's say, by 4 on both sides would be the same as multiplying by 1/4 on both sides, we're just going to call either dividing both sides of an equation by a number or multiplying both sides of an equation by the same number the multiplication property of equality. Those two properties, the addition property of equality and the multiplication property of equality, basically justified every step we were doing when we were using inverse operations in order to solve or isolate a variable, okay? Now, it doesn't mean we don't use other properties along the way, primarily the associative property, the commutative property, and the distributive property. But notice I'm not calling those properties of equality. Those are properties of real numbers and of things like addition and multiplication. Properties of equality basically says, hey, you can add or subtract the same thing from both sides, or you can multiply or divide by the same thing on both sides, and you still have a true equation. So, let's try to justify the steps in solving an equation. So understanding each step. In relatively simple 2-step equations, we can justify each step using one of the properties of equality. All right, so let's take a look at how we do this in exercise number 1. Consider the equation 2x plus 9 equals 21. The steps in solving the equation are shown below. Justify each step. All right. So the first step I would do when solving 2x plus 9 equals 21, thinking about like inverses and things like that, is I subtract 9 from both sides. The justification for that is the addition, we will often abbreviate property as prop of equality. Oh, I I got it in there. Excellent. The addition property of equality. Now again, I get it. We didn't add something to both sides, but you could think of it as adding a -9 to both sides of the equation, and what allows us to do that is the addition property of equality. Then, once we did that and we had 2x equals 12 on both sides, we multiplied both sides by 1/2 or divided by 2, you know, whatever. Okay, and that is the multiplication property of equality. And of course that gave us our final solution, which was x equals 6. All right, simple enough, right? When we add or subtract something from both sides of an equation, that's the addition property of equality. When we multiply or divide something on both sides of the equation, that's the multiplication property of equality. And those are basically it whenever you do a two-step equation, right? And it could be in this order, or it could be in the opposite order, depending on what the steps are to solve the equation. But of course, our equations tend to get way more complicated than this. So let's take a look at more complex equations. When equations are more complicated, we will often use properties of real numbers, such as the commutative, associative, and distributive properties, along with the properties of equality to isolate the variable. So this is going to be a longer one, right? Take a look at this equation. Wow, that's a lot of steps, 7 steps. Okay, so let's take a look at exercise number 2. Consider the equation 3 times x plus 2 minus 2 times x plus 7 equals 4x plus 7. As in the last problem, each step of the solution is shown. Justify each with either a property of equality or a property of real numbers. All right, so you have 5 things you're working with here. The 3 properties of real numbers, those are the commutative and associative properties of addition and multiplication. That's actually 2 of the 3. The distributive property. Then you've got the 2 properties of equality, the addition property of equality, and the multiplication property of equality. What I'd like you to do now is I'd actually like you to look at this and see what you can fill in on these blanks. Take a few minutes. If there's some that you can do and some you can't do, that's cool. If you can get through them all, that's great as well. Take a shot at which property justifies each manipulation, and then we'll talk about them. All right, now one of the tricky things in a problem like this is that you really have to kind of like look at the line before and then look at the next step and say, well, what happened, right? I mean, look at this complicated step that we begin with, and then we have 3x plus 6 minus 2x minus 14 equals 4x plus 7. So what did we do? Well, we multiplied this parentheses by 3, and we multiplied this parentheses by -2, and both of those, right, were the distributive property, right? So that's the distributive property. That down a little bit. All right, so that's simple enough. Now what we have to do is we have to look at this step and compare it to this step. One thing I noticed right away is that the 4x plus 7 hasn't changed at all. And on the left-hand side, what's happened is that 6 minus 2x has become a -2x plus 6. All I did was take the 6 minus 2x and make it into -2x plus 6. In other words, what I did was I took an addition and I flip-flopped it. So that is the commutative property. We're going to do a little abbreviation there. Commutative property of addition. Okay. Then I look at exercise. I look at step number 3. Compared to this, the 4x plus 7 and the 4x plus 7 are the same. So I'm just going to look at that left-hand side. And what I see is I now see x times 3 minus 2, right, plus -8. Now, of course, that -8 just comes from taking the 6 plus -14 and making it into -8. The real question is, what allows me to sort of factor that x out of the 3x plus -2x, making it just x times 3 minus 2? Well, that's our friend, the distributive property. Again, it's kind of the distributive property run in reverse order of what you expect to see it in, but it is still the distributive property. My lovely red pen. The distributive property. Gotta color that in a little bit. Okay, I'm going to bring this up a little bit so we can keep looking at what we've got here. Okay, so then I've got x minus 8 equals 4x plus 7, right? I'm starting to simplify, right? I got a pretty easy looking equation here. The next line, right, has x minus 8 minus 4x plus 8 equals 4x plus 7 minus 4x plus 8, right? So what it appears like I've done is subtracted a 4x from both sides and added an 8 to both sides all at the same time. So I've subtracted a 4x from both sides and added an 8 to both sides. That means I'm using the addition property of equality. All right, so finally, I've got some interaction between the two sides. Okay, so I've got all that, right? Now I'm down to here. I've now taken that 8 minus 4x, right? And I've flip-flopped it to make it 4x minus 8, okay? And likewise, I've done something very similar on this side where I have that 7 minus 4x, and I flip-flopped it to make it negative 4x plus 7. So in both cases, what I've done is I've taken an addition or a subtraction made into an addition, and I reversed the order. Again, commutative property of addition. We do that a lot. We use the commutative property of addition a lot in order to have two like terms sitting by each other so that I can then do something like this, right? I've now taken those negative 8 and positive 8, they've kind of canceled out. That 7 and that 8 have added to be 15. 4x minus 4x, has kind of canceled out. And I pull this trick again where I factor an x out of x minus 4x, right? To get x times 1 minus 4, all right? That is, again, that distributive property. Anytime I factor a variable out or factor a number out, that's the distributive property. And finally, my final step, I've got negative 3x equals 15. I divide by negative 3 on both sides. I get x equals negative 5. What allows me to divide by negative 3 on both sides, almost ironically, is the multiplication property of equality. The multiplication property of equality. If you were to put down the division property of equality, I certainly wouldn't have a problem with that. Your math teacher might, but I certainly wouldn't, because that is a property of equality as long as you don't divide by 0 on both sides. Still, I'm going to stick with the multiplication property of equality. All right, whew. That's a lot of properties, right? And granted, most of the time when you solve an equation, right, you just go through the steps. You're probably not thinking about the properties. You're certainly probably not writing them down, okay? But it's important to know what you're using, why you're using it. It will help kind of solidify in your head what you can and cannot do with equations. All right, now, the rest of this lesson we're going to devote to looking at two very strange cases that occur sometimes when you solve equations. All right, so when we sometimes solve an equation by isolating the variable, strange things can happen. We need to be able to interpret what the math is trying to tell us. So we're going to do two things for the rest of the lesson. We're going to continue to justify steps in solving an equation, and then we're going to interpret these very strange results. Let's take a look at strange case number 1. Stranger and stranger. All right, exercise number 3. Consider the equation 5x minus 3 times the quantity x plus 1 equals 2 times the quantity x plus 4. Letter A asks us to fill in the missing justification in the solution of the equation below. All right, so what I want you to do, I filled in some, like the first one was the distributive property, this one down here was the additive property of equality or the addition property of equality, right? So I filled in these two. What I'd like you to do is try to fill in 1, 2, 3, and then we'll talk about the very strange result we got. Pause the video now. All right, well, after doing that distributive property, right? What this person did is they subtracted 8 from both sides of the equation. That is the addition or additive property of equality. The addition property of equality. All right, great, right? Then here in step 3, we saw this a couple times in the last problem, right? I had 5x minus 3x. I factored an x out of that 5x minus 3x right here, which allows me to combine like terms. That is, again, the distributive property. Lots of red pen. The distributive property. All right, then we subtracted 2x from both sides of the equation. We were already justified that using the additive or addition property of equality, 2 different names for the same thing. And then the last little piece is we then, what do we then do? After we subtracted both from both sides, we got negative 11 equals 0. By subtracting 2x from both sides, that is actually also the additive property of equality. All right, so, right, here we got it, and we've got this like weird, oh, I'm sorry, that's not the addition property of equality. I flip-flopped the 11 minus the 2x. Looking at that going, wait, why would I have the addition property of equality twice? Caught a mistake. Flip-flopped to the negative 11 and the 2x, right, and that was the commutative property. Let me just wipe this out. Look at that, wow. That's the commutative property. Okay, that's a little bit better. Something seemed a little off there to me. All right, now, let's just state the obvious. Something weird is going on here, right? And let's take a look at letter B. The final line of this set of manipulations is a very strange statement. Negative 11 equals 0. Is this a true statement? Could any value of x make it a true statement? Well, pause the video and try to answer that question. So even on its best day, negative 11 doesn't equal 0, right? So that's obviously not a true statement. That's not a true statement, right? Could any value of x make it a true statement? No value of x can make this true, right? And if you think about this, right, what I'm really getting at is, I mean, I could take any value of x I want. X equals 15, x equals negative 3, x equals 52, x equals pi, x equals 3/2. And if I substitute it into this equation, and I played around with it, ultimately speaking, right, I'm going to have something that looks like negative 11 equals 0, right? It's not going to make it true. There's no way it's going to make it true. So letter C, let's take a look at that. What do you think this tells you about the solutions to this equation, i.e. the values of x that make it true? Well, what it tells us is that there are no values of x that make it true, right? Right? There are no solutions. No values make it true. So, equation has no solutions. And that happens sometimes. Sometimes, absolutely no value of x can possibly make an equation true. Right, for instance, let me write down a very, very simple equation. Let's say I had like x plus 5 equals x. I think if you thought about that equation some, forget about subtracting or properties of equality or anything like that, right? If I took any value of x and I plugged it in here, like x equals 2, I'd get 7 equals 2. Doesn't work, right? If I put 10 in here, I'd get 15 equals 10. Doesn't work. Maybe a negative. Maybe I put negative 5 in here. Then I'd get negative 5 plus 5, which would be 0 equals negative 5. Doesn't work. And it doesn't work because the left-hand side is always 5 more than the right-hand side. And there is no value of x that is 5 more than itself. Right? There just isn't. There's no value of x that is 5 more than itself. And therefore, this equation, x plus 5 equals x, can have no solutions whatsoever. It just happens. Now, granted, this is a much more complicated looking equation, and yet, when we got down to this line, 2x minus 11 equals 2x, that was enough for me to know it wasn't going to have any solutions, right? Right at that point, right? Because 2x is just a number, a quantity. So this would be like, oh, there's some number, some quantity, 2x, that's also equal to 11 less than the same quantity. It just doesn't, that can't happen, right? So anytime I work through an equation and I get all the way down and all the x's have gone away, and I get just the most idiotic statement ever, like negative 11 equals 0, I can conclude that there are no solutions to the equation. Now, let's look at another case that is, in a certain sense, the complete opposite. In the last problem, we saw an equation that has no solutions. There's another strange case that could be considered the opposite of that first case. So let's take a look at that in exercise number 4. Consider the equation 7x plus 2 times x plus 5 equals 9x plus 10. Letter A, show that x equals negative 5 and x equals 2 are both solutions to this equation. All right, awesome. Well, you know how to show that things are solutions to equations. I don't want you to solve this equation. I want you to pause the video now, and by substituting in negative 5 everywhere there's an x, I want you to show that it makes the equation true. And then by putting 2 in everywhere for x, I want you to show that 2 makes the equation true. So don't solve it, just show that both values of x make the equation true. Pause the video now and go ahead and do that. All right, let's go through it rather quickly. First things first, let's do x equals negative 5 here. So I'm going to have 7 times negative 5 plus 2 times negative 5 plus 5 equals 9 times negative 5 plus 10. Great. 7 times negative 5 is negative 35. Here I've got negative 5 plus 5, which is 0, and 2 times 0 is 0. 9 times negative 5 is negative 45 plus 10. Negative 35 plus 0 is negative 35, and negative 45 plus 10 is also negative 35. So certainly a solution. Let me put x equals 2 over here. Check that one. So 7 times 2 plus 2 times 2 plus 5 equals 9 times 2 plus 10. 7 times 2 is 14. Here I'll have 2 times 7, also 14. Here I'll have 9 times 2, which is 18, plus 10. 14 plus 14 is 28, and 18 plus 10, also 28. Now, I do want to point out that there's nothing strange about an equation having 2 solutions. Okay? We will see a whole slew of equations in this course that have 2 and exactly 2 solutions. But most of the time, a linear equation, an equation where it's just x to the first, has one and only one solution. Although we did see one in the last problem that had no solutions at all. So the fact that we have a linear equation here that's got at least 2 solutions is a bit strange. So let's take a look at letter B. Solve this equation by manipulating each side of the equation as we did above. What does its final strange result tell you? Okay, so what I'd like you to do is play around with this equation, try to solve it for x, right? You know, use the distributive property, properties of equality, all of that, and see what you get. Pause the video now and go ahead and do it. All right, let's do it. So first thing I'm going to do is I'm going to distribute that 2 through the parentheses. I get 7x plus 2x plus 10 is equal to 9x plus 10. I can combine these like terms and I get 9x plus 10 equals 9x plus 10. And I'm going to pause for a minute right now. Okay, I want you to look at what we have. I've got 9x plus 10 equals 9x plus 10, right? And I want you to just think about what it means for a value of x to be the solution of an equation. I think, given the fact that this expression and this expression are identical to each other, you can probably see now why any value of x is going to solve this equation. I mean, any value. But if you took it a little bit further, you might be tempted to either subtract 9x from both sides or subtract 10 from both sides. Let's subtract 10 from both sides, right? If we subtract 10 from both sides, we'll get 9x equals 9x. And again, side note, that is always true. 9x equals 9x is always true. If I wanted to, I could then subtract 9x from both sides, in which case I'd get 0 equals 0. By the way, 0 is always equal to 0, so that's always true. The point is, this weird result, which we really could stop once we got right here. If you ever have an equation that says, hey, this expression is equal to itself, then what that tells you is that every value of x is a solution. Every value of x is a solution. It also means that there are an infinite number of solutions. So in the last problem, right, we found a situation that could never occur, right? Negative 11 equals 0. That can never happen, and therefore there can never be any values of x that solve that equation. On the other hand, here, as early as this line right here that I've circled, I should be able to say, hey, look, any value of x is going to make 9x plus 10 equal to 9x plus 10. It doesn't matter whether I put 3 in there, 15, negative pi. I can put anything in there, and this is going to be true, which means every value of x is a solution, and there are an infinite number of them. Anyway, if every value of x is a solution, let's take a look at letter C real quick. Test your conclusion in B by picking a random integer, or really any number, and showing that it's a solution to the equation. So, what I'd like you to do now is pause the video, pick a number that, let's say, isn't either one of these two, isn't negative 5 and it isn't 2. Pick any other number, substitute it into the original equation, and show that it's a solution. Pause the video now. All right, well, so many choices. In fact, anything except for the two that we started with, I'm really cool with. You could go with something small, like 0, right? Or you could go with something really big, or you could go with something obnoxious, like 2/3. It doesn't really matter. Let me go with something like 10, whatever. Let me go with x equals 10. All right, I like 10, right? So I get 7 times 10 plus 2 times 10 plus 5 equals 9 times 10 plus 10, right? So 7 times 10 is 70, and I've got 2 times 15. 9 times 10 is 90 plus 10. I get 70 plus 30 is equal to 90 plus 10, and that's 100 equals 100. It's really amazing that we can have equations, right, where every value of x is a solution to that equation. Equations for which that's true are actually given a name. They're called identities, all right? Meaning that the left-hand side is identical to the right-hand side. We just can't really see it right away. The other types of equations, the ones that have no solutions whatsoever, are called inconsistent equations, which kind of makes sense, right? Because we think about an equation as having a solution, right? So if it doesn't, it's kind of inconsistent for what it's worth. You don't need to know those names right now. You'll eventually maybe have to learn them as you go on in math. But for right now, I just need you to know that some linear equations have no solutions at all, and some of them have an infinite number of solutions. Let's wrap this up. So we kind of looked at two sort of different things today. One thing was literally the title of the lesson, justifying the steps used in solving equations. Most of those steps are either the addition property of equality or the multiplication property of equality. But when we're manipulating things on the two different sides to get equivalent expressions, we're also using things like the commutative property of addition, right? The associative property, we didn't see that a lot today, although maybe we didn't, we just didn't use it in terms of a justification. We saw the distributive property quite a few times, especially when we were combining like terms. So all of those you want to know and be able to use to justify what you're doing when you solve an equation. The other topic we looked at, which you also looked at in 8th grade math, were equations that had no solutions whatsoever and equations that had an infinite number of solutions. So the homework is going to give you practice on both justifying steps in solving an equation and also looking for those two special cases. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.